Okay, good morning everyone. I am Andrea Marcucci, I'm a PhD student of Politecnico di Milano, and now I will show you part of my research of my PhD program that is dealing with retrofitting of existing tunnels. Let's start from some motivations. This is the Italian situation. Italy is a country full of hills and mountains, so in order to improve the highways, infrastructures, there was this strong need of building tunnels. So for this reason, it's also the first country in Europe for number of tunnels. The problem is that most of them were built in the past, so in order to avoid their collapse, a large part of them need maintenance intervention. So for this reason, the startup company Hinfra is developing a new maintenance intervention based on extrusion of concrete segments. Here is a video in which you can also see the placement of the reinforcements. Actually, this technology has been avoided and the concrete contains only steel fibers. By the way, the first step is to scrape an existing a layer of the existing tunnels and then to fill the gap with the extrusion, the casting of new concrete. In order to improve this methodology, the startup has also built its own real scale site that is made of rails that guarantee the movement of this steel frame here, in top of which mold that has the shape of the tunnel is built on. There is also this outer mold that is simulating the existing tunnel. So how it works, the frame is moved just below the external mold. In such a way, concrete is pumped from the key of the mold, and as soon as the strength of concrete has developed, the inner mold starts moving backwards. So in this case, on the left, extruding segments of steel fiber reinforced concrete. So here is just a video of how it works, the process. So the velocity, the speed of the mold, it's more or less around 15 millimeters per second, so it's very fast. And the length of each segment is about 1 meter. That is due to also the capacity of the mixer that is not such high to build segments longer than 1 meter. So we are dealing with a additive manufacturing application. As a matter of fact, the material has to satisfy some requirements known as printability requirements. In this case, the pumpability, the extrudability, and the buildability. So, for example, for the first, the material has to show a very low yield stress in order to be pumped through the key of the inner mold. It has to be extruded its entire cross section, so it does not have to remain attached to the mold, and it has to be buildable. So it has to develop in a very fast way the strength in order to also improve the productivity of the methodology. So here is something that I already said. So the concrete is very workable at the beginning, and it has also to show this very fast setting in order to improve the productivity of the retrofitting technique of the tunnel. So here is the state of the art of the material. So at the very beginning it has a very high slump, and after just some minutes it can stand alone. And this is how the compressive strength is increasing. So looking at this graph, we can also recognize three main fields of this material. So up to 30 minutes it is fluid, so it can be tested, for example, through rheometer tests. from 30 minutes up to 1 hour and a half minutes, the material is not longer in its fluid state, even if it's still plastic, and it is developing strength. In fact, after 1 hour, it has already 8 megapascal of compressive strength, and after 1 hour and a half, it's almost in its solid behavior. So mechanical tests are the best way to test this material. So these are some examples of the traditional maintenance of existing tunnels. As you can see, the steps of the retrofitting are quite the same, but so they consist of a scraping of a layer of existing tunnel. Then after placing the reinforcements, there is the very big difference between the two methodologies. Concrete can be or sprayed or also cast. Otherwise, there is also the other solution of the partially precast concrete segments. So on the sustainability, this is a table that highlights the differences between the solution provided by the startup company, the name is Hinfra, and the traditional techniques. So I have divided in materials, construction process, and service life. So from the material point of view, these are two. This is the mixed design of the material, and the very big difference is on the steel. So for the infra, fibers are used, and here only reinforcements are used. For the construction, as I already said, the steps are the same. The very big difference is that the technology of infra is based on automation. So the productivity can be also increased, so the construction rate and the number of workers can be reduced. Speaking of service life, this new maintenance intervention can provide a new service life also larger than 35 years. So I started doing some computations on the sustainability of this intervention, starting from the mixed design. So here there is the comparison between two mixed designs, the one of the company and the one of traditional found in the literature for shotcrete of concrete. As you can see, these calculations are based on this geometry. That is the geometry of the site of the company. We are dealing with a volume more or less of 4 cubic meters. So if you see the density of concrete is 600, so it's quite larger than the traditional one, and of course the global warming potential, that is the equivalency kilograms of CO2 of emission, is larger, but not so much because of the presence of the CSA inside the binder of the infra mixed design. But the very big difference is on the steel. So, for example, the infra technology has a 40 kg per cubic meter of steel fibers, whereas the steel reinforcements here is 90. I will go through this value in the next slide. So if we sum up all the values of the GWP, we can see that the infra has a reduced value. So how did I find the values of the reinforcements? The red curves are the moment, axial force M and domain of a cross section of this shape here. So 40 centimeter of height and 1 meter of length. The length is the segment of the tunnel. So with 40 kg per cubic meter, we have also tested some beams and cubes. We have seen that the compressive strength is about 40-50, and the characterization according to model code of this mixed design has led us to this 8D. So it's quite high tensile strength. So we have seen that this material is able to satisfy satisfy the safety of the tunnel. So how did I found the 90 kg per cubic meter? We have assumed that the equivalent solution with steel reinforcements has to have the same tensile strength, the ultimate limit tensile strength. So doing the computation, we have seen that we have to put a mesh of 12 millimeters, step of 10 centimeters, top and the bottom of the cross section. On the sustainability of the process and service life, it's difficult now to do numerical computations, numerical comparison, because it strongly depends on the case of study. But what we can say is that the productivity, I'm sorry for this, but that should be dashed. So the bottom one is the traditional and the top one is the infra, as you can imagine. So the productivity is very much larger than the other one, and also the service life is strongly larger compared to some existing techniques. So going through the conclusions, Hinfra is proposing a new maintenance intervention for the existing tunnels, consisting of an automated slip forming process. Due to the automation, the productivity is increased and the number of the workers can be reduced. From the mixed design, it's possible to serve a lower CO2 content through the calculation of the GWP, and for a similar capacity, more steel rebars are required compared to the fibers. That result to be a more sustainable solution than one made by Hinfra. So thank you for your attention.